Welcome to a visual tour of Deep Learning Fundamentals, a comprehensive study of neural network theory and optimization. In the next minutes, we will travel from a single neuron all the way to the algorithms that train modern deep networks. First, let us place deep learning in context. Artificial intelligence is the broadest field, the pursuit of machines that exhibit intelligent behavior. Inside it sits machine learning, which builds algorithms that improve from data. Deep learning is a further specialization that uses neural networks with many layers to learn rich, hierarchical representations directly from raw inputs. Every deep network is built from a simple unit, the artificial neuron. Each neuron receives several inputs, multiplies them by learnable weights, adds a bias, and then passes the result through a nonlinear activation function. In short, y equals f of w dot x plus b. This tiny equation, repeated millions of times, is the heart of deep learning. The activation function is what gives a network its expressive power. The sigmoid squashes values into the range 0 to 1. The hyperbolic tangent is similar but centered around 0. The rectified linear unit, or ReLU, simply outputs the positive part of the input and is the most common choice today. Leaky ReLU adds a small slope for negative values to keep neurons alive. Without these nonlinearities, even a deep network would collapse into a single linear transformation. When we stack many layers of neurons together, we obtain a deep feed-forward network. The first layer receives the raw input. Each hidden layer transforms the previous representation, and the final layer produces the prediction. Early layers learn simple features like edges and textures, while deeper layers compose them into increasingly abstract concepts. During forward propagation, information flows from left to right. Each layer computes a weighted sum of the previous activations, adds a bias, and applies its activation function. Layer by layer, the network transforms the input until it reaches the output, where a prediction is finally produced. After the prediction comes the loss, a single number that measures how wrong the network is. Backpropagation then sends an error signal in the opposite direction, from the output back to the input. Using the chain rule of calculus, it computes how much each weight contributed to the error, producing a gradient for every parameter in the network. With those gradients in hand, optimization takes over. Imagine the loss as a curved landscape, and the parameters as a ball rolling on its surface. Gradient descent updates each weight by taking a small step in the direction that decreases the loss. Repeat this for many iterations, and the ball settles into a valley, where the network has learned to make accurate predictions. To recap, a neuron computes a weighted sum followed by a nonlinear activation. Stacking neurons into deep layers lets the network learn rich representations. Forward propagation makes predictions, backpropagation computes gradients, and gradient descent improves the weights. Together, these ideas form the foundation of modern deep learning. Thank you for watching.